Hi there, this is topic 7 for MG5004 and DE5418, and this is for class 2. And what we're going to do today is actually look at how we can use matrices to solve equations, to solve systems of equations. Now what we have here is a matrix A, a column matrix of x, x1, x2, x2, which we can call x, and the answer basically. So what we've got is ax, a times x equals b. So it's not exactly right, but what we can say is that x equals b over a, or more correctly, the inverse of a times b. Now, previously we found the inverse of a, like that, so that x then is the inverse times b. So negative 1 over 35 times all of that. Oops, that's a 0 times 4 to negative 1. And doing the multiplication, we get that x is equal to 2, 3, negative 4, which means that x1 equals 2, x2 equals 3, and x3 equals negative 4. And you would be wise to check those back. So what we've done is we've taken three simultaneous equations, x1 plus 2x2 plus x3 equals 4, and from the second one's 3x1 minus 4x2 minus 2x3 equals 2, and 5x1 plus 3x2 plus 5x3 equals negative 1. Here we have another three linear equations that we need to solve. So we have a system of linear equations that we need to solve, and we can rewrite them as ax equals b, and so that means we're going to write it as 2, negative 1, 3, 1, 3, negative 1, just as being the coefficients of the x terms, 2, negative 1, 5, and that times x1, x2, and x3 is going to equal 2, 11, 3. And we know that ax equals b, so that x is going to be equal to the inverse of a times b. Okay, so we need to start off by finding the inverse of a, which means we need to find the determinant of a. And remember, it doesn't matter which line you work on. So let's do the first row. So it'll be 2 times 3 times 5 minus 1 minus, and then don't forget your signs change. For the next one, it would be 5 minus negative 2, and then plus again, and 3 times negative 1 minus 6. So that would equal, check it out, 14. Now, if we work out the minus, so if we work out a1, we'll just work out a few. That's the determinant of 3, negative 1, negative 1, and 5, which is equal to 14. And then we'll do A12, and that must be equal to, don't forget we need to put the negative outside, so that would be cutting out row 1 and column 2, so that would be 1, negative 1, 2, and 5, which is 5, which is negative 5 minus minus 2, so it's negative 7. And we'll do one more. A13 would be the determinant of, cut out row 1 and 3, so it would be the determinant of 1, 3, 2, negative 1, which would be negative 1 minus 6, which would be negative 7. Okay, so completing that for all of those, we will end up with 14, negative 7, negative 7, 2, 4, 0, negative 8, 5, and 7. Now we need to find the adjunct, which will be the transpose of C. So each row has to become the column. So the first row would become the first column. And the same again, 2, 4, 0. And the third row will become the third column. And then to finish finding the inverse, that's going to be the transpose of C times 1 over the determinant. The determinant we figured out was 14. And then x is equal to the inverse times b, make a little space, so it's equal to negative, positive 1 over 14 times 14 to negative 8, negative 7, 4, 5, negative 7, 0, 7 times b, which is 2, 11, 3, and doing the arithmetic, that comes out as negative 1, 5, 3, and from that we can take that x1 equals negative 1, x2 equals 5, and x3 equals 3. Just a reminder from the previous class of solving linear equations using Cramer's rule, and we will now look at a different way of doing this. Now this is an elimination method. It's kind of similar to the way that you would use if you had two equations and two unknowns. You're going to get rid of one of the variables so that you've then got a much more simpler situation to deal with. So what you do is, to start off with, you take the B matrix and put it in there. Now you'll notice in there that there's been some terribly serious typos in there. The rows, the columns shouldn't be repeated. This should be A1, 2, 2, 2, 3, 2, and this should be 1, 3, 2, 3, and 3, 3. Now we talk about the augmented matrix. That's the one where we've added that extra column. We talk about it, we need to reduce it to a form where it's got a lot of zeros and a lot of ones, and so we're getting rid of several of the variables, so then we can find one of the variables, and once we then find one of the variables we can work backwards to find the others. And here are the requirements that we're looking for. So we want any rows that consist all of 0, that needs to be the bottom row of our matrix. And for a row that's not all zeros, we need the first non-zero element to be 1. and then as you move down the rows, then the 1 needs to move progressively to the right, kind of like we're looking for the identity matrix, kind of. What we're able to do is pretty much anything we like, provided we don't change that idea of equality, as we do with when we solve equations. So what we can do is we can change the order of the lines or the columns. We can multiply or divide a line or a column by some number, and we can add or subtract any multiple of a line or a column to, or I guess from, another line or column. So what we do is we start off with the matrix, we augment it by adding in that last column, then we fiddle around basically until we reduce it to row echelon form, and then we can solve it. And this is called the Gaussian elimination method. These are a few little tricks to give you a clue about what you're doing, and yeah, unless you kind of see one done, it's pretty much stab in the dark. So bearing in mind those rules there, they will give you a pretty good idea of how to work. And what we're looking for is a matrix that's got what we call upper triangular form. You'll see it shortly, and then we can solve it. Now, I hope I've got enough room here. It will take a lot of room, but let's go. So we're going to start off with 2, oops, change color, 2, 3, 4, 1, 2, 3, 1, 4, 5 times x, y, z, and that's 1, 1, 2. Now we can do this there are lots of ways to do it, but this is probably the easiest way for this particular one. What we're going to do is we're going to divide row 1 by 2. So now we've got 1, 3 over 2, 2. Everything else is the same. But we have to divide this other column by 2 as well, only in the first row. Now we've got what we wanted. We wanted to get a 1 in this column here, in this row. So we wanted a 1 in the top left-hand corner. Now we need to move that along. So what we're going to do now is we're going to subtract row 1 from row 2 in row 3. So row 1 is now going to stay the same. Now we're going to subtract row 1 from row 2 for a start. So that'll give us 0, 1/2, 1. So we're subtracting row 1 from row 3. And now we're going to subtract row 1 from row, sorry, that was from row 2. Now we're going to subtract row 1 from row 3. And we're going to do the same in the answer matrix, answer vector as well. Now the next step, we've got our 0 here, which is what we wanted. We've got a 0 there, but we need to turn the next number into a 1. So what we're going to do now is we're going to divide 2 by 1/2, because that'll turn it into a 1. So then we've got 1, 3 over 2, 2. Now we're going to divide the next line by 1/2, so we'll still get 0. Then we'd get 1 and 2. The bottom line is going to stay the same for the moment. So that would be 1, and the bottom line is going to remain the same. Now we need to, oops, that's a 2 transcribed wrongly, that's a 5/2. Now we need the second term in the bottom row to be 0. So what we're going to do is we're going to subtract 5/2 times row 2 from row 3, and that'll give us a 0 in that second element in the third row. So now we've got 0, 0, -2. And do the same to the last element. Now we're nearly there. All we need is a 1 in that bottom right hand corner, and we can get a 1 by dividing row 3 by -2. Do the same for the answer. And now you see we can backwardly substitute to find each of the variables. From the last row we can see that z equals, oops, so I just need to write down that we're going to divide R3 by -2. Okay, you can see how easy it is to make a mistake and lose track of it. That step where I've got -5/2 times R2 from R3, that bottom one should have been -1, like that. And now I'm going to divide that by -2, and I'm going to get positive 1/2 there. So now what we can see is that 1 times z equals 1/2, and then from row 2, so now from row 2, we can see that y plus 2z equals 1. And that gives us, well, we know what z is, so that's y plus 1 equals 1. So y equals 0. And then from row 1, then we've got that x plus 3/2y plus 2z equals 1/2. So we've got that x plus 0 plus 2 times 1/2, which is plus 1, equals 1/2. So x must equal -1/2. Now it's very, 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 very easy to make a mistake, to make an arithmetic mistake. That's why it's, in reality, you need to use something like Excel. But in the exam, you're not going to be able to use Excel, so you need to be able to know how to do it by hand. For this example, what I'll do is I will give you the steps and see if you can get the answers. Okay, the first step is to take R2 and subtract from it 2 times R1, and at the same time find R3 minus R1. And then step 2, then I want you to take R2 and divide it by 3, and then add that to row 4 as well. and then I want you to divide R3 by -2, and at the same time divide R3 by -3 and add that to row 4, and then we should have ended up with 1, 2, 3, 1, 0, 1, 5/3, 1/3, 0, 0, 1, 1/2, and 0, 0, 0, 2. Now what should that equal? That should equal 5, 7/3, 1/2, -2. And then you can work back. Actually, there's a fourth step there. You should have, of course, divided R4 by 2. So then that should be 1, and that should be -1. We'll do this one in class. What we'll be doing is we'll be setting it up as an augmented matrix, as I mentioned before. We'll set it out like that, but we'll do that one in class. Again, as on the previous slide, we will set it up as the augmented matrix. Like that. And then we'll start. Okay, what we need to do is we need to eliminate the x1 coefficients from the second and third row, and we're going to do that by subtracting 2/1 times the first row from the second row and 3/1 times the first row from the third row, so that then our matrix becomes 1, and it's got the required zeros in the right place. And then the next step is to subtract from the third row 14/9 times the second row. Right, so we're going to subtract from the third row 14/9 times the second row. And if we do this, the matrix becomes Now, we could continue and do the last step and divide the last row by -4 1/3, but we probably don't need to. So now we can put it all back together. So we've got 1, -4, -2, 0, 9, 6, 0, 0, -4.33 times x1, x2, x3 equals 21, -39, -4 1/3, And now we can backwardly work out that -4 1/3 x3 equals -4 1/3. So x3 equals 1. And now we can use that to figure out x2, because 9x2 plus 6 times x3, but we know that that's 1, is equal to -39. So that tells us that x2 is -5. And then we can use all of those to work out x1. So we'd have that x1 minus 4 times -5, because that's x2, minus 2 times 1, because that's x3, and that equals 21, and that can tell us that x1 is equal to 3. So these are solutions. x1 is equal to 3, x2 equals -5, and x3 equals 1. And it would be a good idea if you checked that. The first step would be to shift everything onto the left-hand side. So then we have 9 plus j12 times I1 minus 6 plus j8 times I2 minus 5 equals 0, and -6 plus j8 times I1 plus 8 plus j3 times I2 minus 2 plus j4 equals 0. Okay, let's do this by Cramer's rule. So now we have that I1 over the determinant of this is going to be equal to -I2 over the determinant of and that's going to equal I over determinant of 9 plus j12 minus 6 plus 8j or j8 and -6 plus j8 and 8 plus j3. Okay, just a little bit of work behind the scenes. So now we've got that I1 is over 20 plus j55 equals -I2 over -j100 equals I over 64 plus j27. From that then we can find that I1 is equal to 20 plus j55 over 64 plus j27, and probably the easiest way to do that is to convert it to polar and then use polar division. So using your calculators, R would be 3425, angle 70.02, sorry, divided by the square root of 4825, angle 28.27, and then if we do the division, I1 is equal to 0.84. Oops, for angle 47.15, and that's in amps. And similarly, we can find that I2 is going to equal negative J100, which is 100 angle 90 over, and we've already worked out what 64 plus J27 is. That's root 4825 angle 22.87, and do that division. 1.44 angle 67.13 amps. Matrices are of great importance just for themselves, but as far as you're concerned, their practical importance lies in the solution of sets of linear equations. Lots of these sets exist, and so it's a wide range of scientific and engineering contexts that they exist in. So let's just have a little bit of a look at the end of this. We talk about trivial solutions and non-trivial solution, and we could say that a trivial solution is x is equal to 0, but ax equals 0 has a non-trivial solution if and only if the determinant of a is equal to 0. Let's have a look at some examples. Let's have a look at 2x plus y equals 5, x minus 2y equals negative 5. So 2, 1, 1, negative 2 times x, y equals 5, negative 5. The determinant is negative 4 minus 1, which is negative 5, which is clearly not 0. So we can say that there is a solution so the system has a solution, and in fact x equals 1, y equals 3. Here's another example. 2x plus y equals 0, and x minus 2y equals 0. The determinant is still equal to negative 5, but in this case b is equal to 0, so there's a trivial solution of x equals 0, y equals 0. Let's do some more examples of this. Let's have a look at negative 3, 6, 1, negative 2. Equals 15, 5. The determinant of a is 0 and b doesn't equal 0, so the inverse of a doesn't exist. And if you think about how we find the inverse, we'd be wanting to do 1 over the determinant, and if the determinant's 0, it doesn't work. So there's going to be a problem solving this set of equations, and that's basically because the second equation is negative 3 times the first one. So all we could do as a solution would be to say that x equals 2t for some constant minus 5, and y was equal to some number. It's not going to give us a unique solution. It's a bit of an issue. Another example, the determinant again is 0, and obviously b is not 0. Firstly, the first, sorry, getting a bit tongue-tied there. If you look at the left-hand matrix, the first line is -3 times the second line, but on the right-hand side, it's only -2 times the bottom line. So it's inconsistent. So there's no solution. And one last one. The determinant is 0, and in this case b is equal to 0 as well. So there's an infinite number of solutions. And the best that you can do is to say that, well, for any number s, that x would be 2s and y would be that number. Eigenvalues and eigenvectors, for example, describe the frequency and mode of vibration respectively, and in mechanics they represent the principal stresses and the principal axis of stress in bodies that are subjected to forces. Eigenvalues play an important part in looking at the stability of dynamic systems, and so they're central to the evaluation of energy levels in quantum mechanics and quantum physics. So what we've got there is that we need to find the values of the eigenvalues, the lambda, and what we're looking for is lambda such that a minus lambda times the identity times x is equal to 0. Or putting that another way, we're looking for ax equals lambda x. Oops, need that to see like that. So to have a non-trivial solution, 0 has got to equal a minus lambda times I, and what we're looking at here is 3 minus lambda, 1, -2, and negative lambda. And we talk about this a minus lambda I, oops, fell over, as being the characteristic equation. Now I'll do this example in class. So I'll take the room to work out the one above. Okay, so let's work out the determinant of what we've got there. So 3 minus lambda times negative lambda minus -2 times 1 has got to equal 0. So 0 equals -3 lambda plus lambda squared plus 2. So we can factorize that and say that lambda minus 2 times lambda minus 1 equals 0. So it's got non-trivial solutions only if lambda equals 1 or lambda equals 2. Now, if lambda equals 1, then our matrix becomes 2, 1, -2, -1. and so then x is equal to, well, xy, and it's going to be some number times 1, negative 2, and if lambda equals 2, then our matrix is going to become 1, 1, negative 2, negative 2. So our x is going to be some number times 1, negative 1. So the lambda is the eigenvalue, and this x is the eigenvector. Now remember what we're doing. What we're doing is we need to find the determinant of a minus lambda times I, and we need to multiply that by x. So let's do that. Let's find the characteristic determinant. So in this case it will be 2 minus lambda, 3 negative 2, 1, and 4 minus lambda, negative 2, and 2, 10, negative 5 minus lambda. Now if we're going to expand this, it will become 2 minus lambda times, now we need to be very careful, 4 minus lambda times negative 5 minus lambda, minus 10 times negative 2, 0 minus negative 2, so it would be negative 20, so minus negative 20, minus 3 times 1 times negative 5 minus, negative 5 times lambda, so that's times 1, minus negative 4, plus negative 2 times 5 times 2, whoops, erasing, and that minus, so 10 minus 2 times 4 minus lambda. And if we deal with all of that, then we're going to get 2 minus lambda times lambda plus 1 minus 1 plus lambda, and if we deal with that, we will get 1 plus lambda times 2 lambda minus lambda squared minus 1, and even further we can factorize it to that. Now the characteristic equation then is multiplying by negative 1 does nothing, so the characteristic determinant is going to be 1 plus lambda times 1 minus lambda squared equals 0. So the eigenvalues are going to be negative 1 and 1. The characteristic equation this time, the characteristic determinant, is going to be 2 minus lambda 0, 1, negative 1, 4 minus lambda negative 1, negative 1, 2, 0 minus lambda or negative lambda, and that's got to equal 0. So as before, 2 minus lambda, actually that's a lambda, not an x, times 4 minus lambda times negative lambda minus negative 2 plus 1 times negative 2 minus negative 1 times 4 minus lambda, because there's no middle term because because I've got a 0 there, and that's got to equal 0. So 2 minus lambda, and what have we got left? If we expand all of that, and we've got a common factor of 2 minus lambda, out of the first term, we've got lambda squared minus 4 lambda plus 2 plus 2 minus lambda equals 0. So 2 minus lambda, and if we take it all out and factorize it, then we get lambda squared minus 4 lambda plus 3 equals 0. So then we can factorize the curly bracketed term. Then we have 3 factors. So lambda equals 1, 2, or 3. Now for lambda equals 1, then the vector becomes 1, 0, 1, negative 1, 3, negative 1, and negative 1, 2, negative 1, times x1, x2, x3 equals 0. And from that we get that x1 plus, from the first line, x3 equals 0. So x3 equals the opposite of x1. And from row 2 we get that negative x1 plus 3x2 minus x3 equals 0. And don't forget, we already know what x3 is. So now we have negative x1 plus 2x2 plus another x1 is equal to 0. So that means x2 is equal to 0. So x1, if I can squeeze it in up here, I think. So x1, so that won't be, it'll be the big x1, it'll be the x1 will be 1, 0, negative 1. That is an eigenvector corresponding to lambda equals 1, or lambda 1 equals 1. I'll do the rest on the next page. Similarly, for lambda equals 2, then we generate the matrix. And then we get ourselves a series of equations, and we can start off with that x3 is equal to x3 is equal to 0, because it's 0x1 plus 0x2 plus 1 times x3, so x3 is equal to 0. Then from the second line it's negative x1 plus 2x2 minus x3 equals 0. We already know x3 is 0, so 2x2 minus x1 equals 0, which is all we can tell is that x1 equals 2x2. So an eigenvector corresponding to lambda 2 equals 2 is going to be 2, 1, 0. Similarly, for lambda 3 equals 3, we can do the same process and we can work out that x3 is equal to 1, 2, 1. So the corresponding eigenvector to lambda 3 equals 3 is 1, 2, 1. We will do this one in class.